This video reviews the calculation of the fraction of a species at equilibrium. Now, this is something that we like to do after we have introduced and understood equilibrium constants, and it's just an application of the power of having an equilibrium constant. Alright, so let's think about a very simple reaction, and what I'm going to show right here actually only applies to reactions with one reagent and one product, and those tend to be isomerization reactions. Okay, so let's think about a process that is A to give B, and we're going to assume that these are solutes in ideal dilute solutions. Right, so quintessential example of this reaction would be the isomerization of glucose 6-phosphate to fructose 6-phosphate, which is the second step in glycolysis that takes place in our cells. Alright, so what we're trying to calculate is called the fraction of the product at equilibrium. And that has a very simple definition. The fraction at equilibrium, which we're going to call f of eq, is simply the concentration of the product at equilibrium over the total concentration at equilibrium. Concentration of B at equilibrium. Okay? Alright, so now this fraction at equilibrium provides really useful information. For example, if that number is very large, right, that means that most of the equilibrium composition is dominated by products. But if that fraction of the equilibrium is very small, then that means that the reaction has not gone very far at all. The equilibrium is very displaced towards reagents instead. Okay, so our question then is, how do we actually get this from the equilibrium constant? Okay, so if we write the equilibrium constant for this process, that would be the activity of B over the activity of A, and that is simply the ratio of the molar concentration of B at equilibrium over 1 molar, which is the reference concentration, and then the concentration of A at equilibrium over 1 molar, and then we simply write this as B over A at equilibrium. Okay, right, so the question is, how does knowledge of the equilibrium constant inform the calculation of the fraction of equilibrium? Okay, so it's very simple to see that if you divide this expression over the concentration of reagents, then you're going to be able to do that very nicely. Alright, so that will be the concentration of B at equilibrium divided over the concentration of A at equilibrium, and then here you will have the concentration of A at equilibrium over the concentration of A, and then B over A. Okay, this term is very simple, that just reduces to 1, and then notice that these two terms are simply the equilibrium constant. Okay, so what we have right here is that you get to an expression that looks like this, k 1 plus k. Alright, so notice how simple it is to just use your knowledge of the equilibrium constant to be able to find that fraction of equilibrium. Let's try to do a numerical example to just illustrate again how simple this is. Okay, so now we're going to consider that these are the actual fructose 6-phosphate and glucose 6-phosphate, which I can write simply as G6P and then F6P. And we actually know that the reaction Gibbs energy for this process under the standard state is plus 1.7 kilojoules per mole. Okay? So from there, we just have to calculate what the value of the equilibrium constant is, and notice that K is going to be equal to E to the minus delta RG M naught over RT. Right, so plugging in here that number, and then using here 298 Kelvin, we get to a value of the equilibrium constant of 0.50. Okay, notice that this makes perfect sense, right? You have a positive value for the reaction Gibbs energy. What that actually means is that the reaction is not very displaced towards products. Instead, it's actually much more displaced towards reagents at equilibrium. And you can see that because the value of the equilibrium constant is less than 1, right? And again, that means that signifies that this reaction is actually not going to proceed dramatically towards fructose 6-phosphate. Instead, is actually going to be, that equilibrium is going to be reached when you still have a lot of concentration of glucose 6-phosphate around. Let's actually calculate exactly how much, right? So that fraction at equilibrium is gonna give us that number very nicely, right? 1 plus 0.15, and this is 0.33. All right, so this is what this number conveys, right? What that means is that 33% of the species that you have at equilibrium are products, and the remaining are reagents, right? So 67% will be reagents approximately. Okay, so again, these are really nice numbers to really deeply understand what is going on at equilibrium, right? Which one is dominating. So let's summarize here what's going on here. Right, notice that you have here a positive sign for the molar reaction Gibbs energy. That is bad news if you want to have a reaction that is very displaced towards products. Okay, and we can see that because the equilibrium constant is less than 1, that's also bad news, and that can be further corroborated by this relatively low fraction of products at equilibrium, right? The reaction is not even half complete, right? Instead, you reach equilibrium by the time that the reaction mixture reaches 33% completion, right? So 33% concentration of products compared to 66% concentration of reagents.